Somewhere in this galaxy there is a star that should not exist. Not because it defies physics, not because our instruments misread it, but because everything we understand about stellar evolution, about how stars are born and how they die, about the absolute upper limits of what nature is permitted to build, this star breaks all of it. Its name is R13601, and for decades, astronomers assumed something like it was simply impossible. The numbers attached to this object are not poetic exaggerations. They're not rounded for effect. At roughly 200 times the mass of our Sun, R13601 produces more energy in a single second than our Sun will emit across an entire year. Its surface burns at 46,000 degrees Kelvin, nearly 8 times hotter than the star that gave us life. And at its peak luminosity, it blazes at approximately 8.7 million times brighter than the Sun. 8.7 million. That is not a typo. And yet the most terrifying thing about R13601 is not what it is right now. It is what it is becoming. Because stars this massive do not simply age. They do not quietly fade. They build towards something catastrophic. If space fascinates you, a like and subscribe means everything to us. Let's begin. To understand why R13601 is so profoundly alarming, we first need to understand the system it inhabits, and the world we thought we knew before it was discovered. For most of modern astronomy, the concept of stellar mass had a ceiling, not an arbitrary one, a physical one, a hard limit imposed by the universe itself, written into the mathematics of radiation pressure and gravitational collapse. And that limit was known as the Eddington limit, named after the British astrophysicist Sir Arthur Eddington, who in the early 20th century calculated the theoretical maximum luminosity a star of a given mass could achieve before its own radiation tore it apart from the inside. By the mid-20th century, the consensus among stellar physicists was relatively settled. Stars could not exceed approximately 150 times the mass of the Sun. Any protostellar cloud attempting to collapse into something larger would simply be blown apart by its own energy before it could finish forming. The universe, it seemed, had a cap on its ambitions. Then we pointed the right telescope at the right corner of the sky. The Large Magellanic Cloud is a satellite galaxy of the Milky Way, visible to the naked eye from the southern hemisphere as a faint smear of light roughly 160,000 light-years from Earth. It is close enough for our instruments to resolve individual stars, and inside it, within a region called the Tarantula Nebula, one of the most ferociously active star-forming regions in the observable universe, sits a cluster of stars so densely packed, so luminously violent, that early observations could not separate its components at all. That cluster is called R136, and what we thought was a single extraordinarily bright object turned out to be something far more extraordinary. An entire nursery of monsters. R136 sits at the heart of the Tarantula Nebula, embedded in 30 Doradus, a region of ionized hydrogen gas stretching hundreds of light-years across. The nebula itself is named for the spider-like filaments of glowing gas that radiate outward from its core, tendrils of stellar wind and radiation sculpted by the energy pouring from the stars within. If the Tarantula Nebula were as close to Earth as the Orion Nebula, its most familiar counterpart in our sky, it would cast shadows on the ground at night. It would be bright enough to read by. In the 1980s, astronomers using ground-based observatories began to suspect that something unusual was happening inside R136. The integrated brightness of the cluster was off the charts, producing ultraviolet radiation at a rate that strained credibility. Initial interpretations suggested it might be a single hypermassive star, something in the range of 1,000 to 2,000 solar masses. That idea was eventually ruled out. What replaced it was almost more unsettling. It was not one star, it was dozens of them, all of extraordinary mass, all burning at temperatures that beggar comprehension. And at the centre of that cluster, outshining everything else in the immediate stellar neighbourhood, was R136A1. Confirmed measurements using the Hubble Space Telescope, specifically observations carried out in 2010 by a team led by British astrophysicist Paul Crowther of the University of Sheffield, pinned R136A1's mass at somewhere between 265 and 315 solar masses at birth, having already shed significant material through its ferocious stellar winds. Current mass estimates place it at around 200 to 220 solar masses. Even after burning off the equivalent of dozens of full suns worth of material, it remains the most massive star ever confirmed by direct observation. Crowther's team published their findings in the monthly notices of the Royal Astronomical Society in 2010, and the response from the scientific community was not quiet validation. It was controlled shock, because R136A1 did not just exceed the theoretical 150 solar mass limit, it shattered it by more than a factor of 2. What does it look like, standing in the data if not in person? Imagine our Sun, that yellow dwarf 93 million miles away, 865,000 miles in diameter, the gravitational anchor of our entire solar system, the engine of all life on Earth. Now imagine something so much larger that if you placed R136A1 at the centre of our solar system, its outer atmosphere would swallow Mercury, Venus, Earth, and Mars without disruption. It would extend well into the asteroid belt. The Sun, to R136A1, is roughly what a marble is to a hot air balloon. Its diameter spans approximately 30 to 35 times that of the Sun. Its surface temperature approaches 46,000 degrees Kelvin at the photosphere, the visible surface, compared to the Sun's 5,778 degrees Kelvin. At those temperatures, R136A1 blazes most intensely in the far ultraviolet, a range of the electromagnetic spectrum that is invisible to human eyes but devastating to molecular bonds. Ultraviolet radiation from R136A1 alone is responsible for ionizing enormous regions of the surrounding nebula, stripping electrons from hydrogen atoms across distances measured in light years, and its luminosity, the total energy output across all wavelengths, sits at approximately 8.7 million times that of the Sun. Some revised estimates push it toward 9 million solar luminosities. Numbers like these are not merely statistics, they are descriptions of a force so concentrated, so relentless, that it physically reshapes the space around it. But here is where we encounter the first of many paradoxes surrounding this object. R136A1 should not still exist in its current form. Stars of this mass burn through their hydrogen fuel at an almost incomprehensible rate. Where the Sun converts roughly 600 million tons of hydrogen into helium every second through nuclear fusion, R136A1 is burning through material at hundreds of thousands of times that rate. Its estimated lifespan, from formation to death, is thought to be on the order of just 2 to 3 million years. To put that in perspective, our Sun is approximately 4.6 billion years old and is only halfway through its life. R136A1 will live for less than 1/2000th of that time. In cosmic terms, this is not a star with a lifespan, it is a star with a deadline. Estimates from stellar evolution models suggest R136A1 formed somewhere between 1 and 2 million years ago, which means we are not observing this star in infancy. We are observing it somewhere near the midpoint of its brief, furious life. The stellar clock is running, and what waits at the end of that clock is not the quiet white dwarf our Sun will eventually become, not the gentle planetary nebula it will shed into the void. What waits at the end of R136A1's life is something that has been theorized but rarely, if ever, directly confirmed from beginning to end, a pair instability supernova, or possibly something even more extreme, a hypernova with a black hole remnant of almost unimaginable mass. But that is not the full story, because before we get to what R136A1 will become, we need to understand what it is doing right now, to itself, to its neighbours, and to the space around it. Because R136A1 is not a passive object. It is actively, violently, continuously destroying itself, and in doing so, it is making the surrounding universe a fundamentally more dangerous place. There is a concept in astrophysics called the stellar wind. It sounds almost gentle. A wind. Something rustling through cosmic grass. The reality is something else entirely. Every star sheds mass. Our Sun loses approximately 1 to 2 million tons of material per second through its solar wind, a stream of charged particles flowing outward at speeds of 400 to 800 kilometers per second. That sounds significant, and for the purposes of planetary atmospheres and magnetospheres, it is. But in the context of stellar evolution, the Sun's mass loss rate is negligible. Over its entire 10 billion year lifespan, the Sun will lose less than 1% of its total mass to stellar wind. Now consider R136-1. Mass loss rates for Wolf-Rayet-type stars and extreme O-type supergiants, the categories R136-1 occupies simultaneously, are measured in solar masses per million years. R136-1 is currently shedding the equivalent of roughly one solar mass every 5,000 to 10,000 years. At that rate, it is actively losing more mass in a single century than our planet has in its entire body. The stellar wind from R136-1 flows outward at speeds exceeding 2,500 km per second, roughly 1.5 million miles per hour. This is not wind. This is radiation-driven ablation. The star is evaporating itself into space, and the consequences of this evaporation are written across the Tarantula Nebula in glowing letters of ionized gas. The stellar wind from R136-A1 and its immediate neighbours in the R136 cluster has carved an enormous cavity in the surrounding molecular cloud, a bubble of superheated, nearly evacuated space stretching dozens of light-years across. The material that once occupied that bubble has been swept up into a dense shell at the edges, glowing brilliantly in H-alpha light, yet visible to our telescopes as the intricate filamentary structure that gives the Tarantula Nebula its characteristic appearance. R136-1 is not just a star, it is an ecological force, reshaping the large-scale structure of the gas and dust that surrounds it, compressing some regions into new star formation, destroying the conditions for star formation in others. It is simultaneously a creator and a destroyer, and it cannot distinguish between the two. Now here is where it gets truly strange. The mass loss process for a star like R136-1 is not smooth or predictable. It is violent, episodic, and in some cases catastrophic on scales that are difficult to overstate. Among the class of stars known as luminous blue variables, or LBVs, the category R136-1 may transition through during its evolution. There are eruption events called giant eruptions or LBV outbursts, during which a star can shed the equivalent of several solar masses in a matter of years or even months. These are not explosions in the conventional sense. The star does not detonate, but its outer layers become unstable, inflating and ejecting material at rates that briefly approach the mass loss rates of a supernova, without the star actually dying. The most famous example of this behaviour in our galaxy is Eta Carinae, a massive star system in the Carina Nebula, approximately 7,500 light-years from Earth. In the 1840s, Eta Carinae underwent the Great Eruption, a decades-long outburst that made it briefly the second brightest star in the night sky, behind only Sirius, yet despite being 250 times farther away than Sirius is from Earth. During this eruption, Eta Carinae ejected somewhere between 10 and 40 solar masses of material, which now forms the famous Homunculus Nebula, a bipolar shell of gas and dust surrounding the star, still expanding outward today, at speeds of 650 km per second. Eta Carinae offers us a preview. R136-1, more massive by a substantial margin, occupies a region of stellar evolution where eruptions of this kind are not just possible, they are, on the right timescales, almost inevitable. What happens to a star's neighbours during an LBV eruption? The short answer is, nothing good. The ejected shell of material, travelling at hundreds of kilometres per second and carrying the energy of years of accumulated radiation, propagates outward through the surrounding interstellar medium like a shockwave. When it encounters denser regions of gas and dust, it compresses them, potentially triggering new episodes of star formation. When it encounters other stellar systems, it strips away their outer envelopes, blasting away planetary atmospheres and disrupting planetary orbits. R136 is not a lonely cluster. It is one of the most densely populated stellar environments in the local group of galaxies. Within a sphere just a few light-years across at its core, dozens of massive stars are crammed together, their winds, their radiation fields, their gravity all interacting in ways that create a genuinely chaotic physical environment. This is not a neighbourhood, it is a storm system. The interactions between stellar winds in a cluster like R136 create what astrophysicists call a cluster wind, a collective outflow driven by the combined mechanical energy of all the stellar winds within the cluster. This cluster wind can reach velocities and pressures far exceeding what any individual star can produce alone. It creates a collective bow shock, a zone where the cluster wind meets the surrounding interstellar medium, and both are abruptly decelerated, heating the shocked material to temperatures of tens of millions of degrees, generating X-ray emission that has been directly detected by space-based observatories. The Chandra X-ray Observatory has mapped this emission in detail. The Tarantula Nebula glows in X-rays across a region hundreds of light-years wide, a visible marker of the ongoing violence at its heart. R13601 and its siblings are not merely lighting up the surrounding gas, they are irradiating it, shocking it, ionizing it, turning a once cold molecular cloud into a plasma cauldron. This means that any planet orbiting any star within a significant radius of R136 is not merely in an inhospitable environment, it is in an environment so energetically hostile that the conventional metrics of habitability become essentially meaningless. The ultraviolet flux alone from R13601, at the distances where the nearest cluster members orbit, would be sufficient to strip an unmagnetized planetary atmosphere within geological timescales. Complex chemistry, the kind that produces amino acids that builds the precursor molecules of life, would be continuously disrupted, broken apart before it could accumulate. R13601 is not just dangerous to any hypothetical biosphere within the cluster, it is dangerous to the concept of biological complexity in its immediate cosmic neighbourhood. But let us pull back from the local scale for a moment, because the implications of R136A1's existence extend well beyond its immediate environment. What does it mean for galactic evolution that stars this massive can form at all? The Tarantula Nebula's unusual character, its extraordinary star formation efficiency, its population of extreme objects, is directly related to the metallicity of the Large Magellanic Cloud. Metallicity, in an astronomical sense, refers to the abundance of elements heavier than helium in a given environment. The Large Magellanic Cloud is relatively metal-poor compared to the inner Milky Way. And metal-poor environments, counterintuitively, are more permissive of extreme stellar masses. Here is why. Metals, carbon, oxygen, silicon, iron, are extraordinarily efficient absorbers of radiation. In a high metallicity environment, a protostellar cloud forming around a nascent massive star will be subjected to intense radiation pressure transmitted through its metal-rich dust and gas. That pressure acts as a brake, limiting how much material can pile onto the forming star before the radiation force reverses the infall. In a low metallicity environment, that brake is weaker. More material can accrete. The star can grow heavier before the feedback mechanism halts its growth. This has a profound implication for the early universe. In the first few 100 million years after the Big Bang, the universe contained almost no metals. Hydrogen and helium dominated, with trace amounts of lithium. The first generation of stars, designated population 3 stars by astronomers, formed in this pristine, metal-free environment. Theoretical models of population 3 star formation predict that these objects reached masses of hundreds to potentially thousands of solar masses. They were, if our models are correct, the most extreme stellar objects in the history of the universe. They lived for perhaps 1 million years, then died in cataclysmic explosions that seeded the surrounding intergalactic medium with the first heavy elements ever produced. We have never directly observed a population 3 star. They are gone. Their light has long since passed us by, shifted into the infrared by the expansion of the universe over 13 billion years. But R13601, formed in a low metallicity environment roughly analogous in some ways to conditions in the early universe, gives us the closest observable proxy we have. It is an echo, imperfect and incomplete, of stellar physics that dominated the cosmos before the Earth existed, before the solar system existed, before any of the familiar structures of the modern universe were in place. Looking at R136A1, in a meaningful sense, is looking backward in time, not through distance alone, but through the history of stellar physics. What did the early universe look like when it was filled with objects like this? Brighter, harder, more violent. The first billion years of cosmic history were not the gentle, expanding darkness we sometimes imagine. They were lit by stars far more extreme than anything that exists today in our immediate corner of the galaxy. The universe began in brilliance so total that the concept of a dark sky would have been alien, and then those stars died, and the metals they created changed the rules. The universe's ability to build its own most extreme objects was progressively diminished by the legacy of those objects' deaths. R13601 exists in a small pocket of the modern universe, where the old rules still partially apply. A remnant environment, a fossil of early cosmic physics, still burning, still violent, still defying the limits that the universe has spent billions of years constructing. The implications of this discovery are almost too vast to comprehend, but we have not yet reached the heart of what makes R136A1 truly terrifying. Because we have been talking about what this star does while it lives, we have not yet fully reckoned with what it will do when it dies. Every star dies. This is one of the most fundamental and sobering truths in all of astrophysics. The Sun will die, Betelgeuse will die. The most distant quasar we can observe is powered by a process that will eventually exhaust itself. On a long enough timeline, all stellar furnaces go cold. But the manner of death depends entirely on the mass of the star, and mass in stellar astrophysics is destiny. For stars like our Sun, from roughly 0.8 to 8 solar masses, the death sequence is well understood and, in a cosmic sense, relatively benign. The core exhausts its hydrogen fuel, fusion moves to a shell around the core, the outer layers expand enormously, turning the star into a red giant. Eventually the core contracts into a degenerate ball of carbon and oxygen, a white dwarf, while the outer layers drift away into space as a planetary nebula. Quiet, dispersed, poignant in the way that endings always are. For stars between roughly 8 and 20 solar masses, the ending is more violent. The core does not just contract, it collapses, catastrophically, in less than a second, as electron degeneracy pressure is overwhelmed by gravity. The outer layers, still falling inward at the moment of core collapse, bounce off the newly formed neutron star and are ejected at a significant fraction of the speed of light in a core collapse supernova. Energies on the order of 10 to the 44th power joules are released, more energy than our Sun will emit across its entire 10 billion year lifespan. Air is deposited into the surrounding interstellar medium in a matter of seconds. For stars above approximately 20 to 25 solar masses, even that dramatic end is insufficient. The core collapses directly into a black hole. The outer layers may still explode in a supernova, or they may fall back and be swallowed. The remnant is not a neutron star. It is a singularity, a point of infinite density wrapped in an event horizon, beyond which nothing, not matter, not light, not information, can escape. Now consider what awaits R13601 at 200 solar masses and climbing in theoretical menace. At masses above roughly 130 to 150 solar masses, stellar physicists encounter a different kind of instability. Not the standard core collapse sequence, something more fundamental, more catastrophic, rooted in the exotic physics of the stellar core at extreme temperatures. As the core of a very massive star heats beyond approximately 3 billion degrees Kelvin, the thermal photons, the gamma rays generated by the furious fusion reactions, begin to lose energy to a process called pair production. At these temperatures, high-energy photons spontaneously convert into electron-positron pairs. This is not a minor energy drain. It is a catastrophic reduction in the radiation pressure that has been supporting the star's core against gravitational collapse throughout its entire life. When pair production begins in earnest, the core loses pressure support. It contracts rapidly. The contraction heats the core further, driving more pair production, reducing pressure further. This is a runaway instability, a feedback loop with no natural break. The core begins a freefall collapse, but then something remarkable and terrible happens. The collapse ignites explosive oxygen and silicon burning at a rate so intense that the energy released, in a fraction of a second, is enough to reverse the collapse entirely, not just arrest it, reverse it. The star rebounds in a thermonuclear explosion of almost unimaginable scale. This event is called a pair instability supernova, and it is categorically different from a core collapse supernova in ways that matter enormously. In a core collapse supernova, a neutron star or black hole remnant is left behind. The star dies, but something remains. In a pair instability supernova, there is no remnant. The explosion is so complete, the energy so perfectly sufficient to unbind every layer of the star that the entire object is destroyed. Completely. Nothing left but an expanding cloud of heavy elements, the enriched stellar interior, the products of a lifetime of nuclear burning scattered across dozens of light years of interstellar space, complete, total, annihilating. The energy released in a pair instability supernova is staggering even by supernova standards. While a core collapse supernova deposits roughly 10 to the power of 44 joules in kinetic energy into its ejector, a pair instability supernova can release up to 10 to the power of 45 joules in kinetic energy, 10 times more powerful, while simultaneously generating a burst of optical and ultraviolet luminosity that can outshine an entire galaxy for weeks to months. We've observed objects we believe to be pair instability supernovae. The most compelling example in recent astronomical history is SN 2006 GY, detected in 2006 in the galaxy NGC 1260, approximately 238 million light-years from Earth. At its peak, SN 2006 GY was roughly 50 billion times brighter than the Sun. It was the most luminous supernova ever observed at the time of its discovery. It remained visible to telescopes for months, long after most supernovae would have faded to obscurity. Its light curve, the way its brightness changed over time, was incompatible with a standard core collapse mechanism. The energy budget required a different engine. Pair instability was, and remains, the leading explanation. But here is the complication for R13601 specifically. At exactly 200 solar masses, a star does not necessarily undergo a simple, clean pair instability supernova. The mathematics becomes messy. At certain mass ranges, roughly 100 to 130 solar masses, pair instability is expected to trigger repeated pulsational events, giant eruptions that shed mass in violent waves before a final explosion. This regime is called pulsational pair instability, and it produces a sequence of dramatic outbursts that can make the star briefly as bright as a supernova before it restabilizes, sheds more mass, and eventually dies in a final explosion. At masses above approximately 130 solar masses, the full pair instability supernova is predicted. At masses above 250 solar masses, which current estimates suggest R13601 may have exceeded at birth, the calculations diverge into territory that is theoretically exciting and observationally underexplored. Some models suggest that stars at extreme initial masses collapse directly into black holes without a visible explosion at all, the so-called failed supernova scenario, where the star simply disappears from the optical sky, its light replaced only by a brief X-ray or neutrino signature. The mass falls inward, the black hole forms, and the star is gone. Gone, not with a bang, but with an absence. What kind of black hole does a star like R136A1 leave behind if it collapses without fully dispersing? Even accounting for mass loss, the remnant black hole could potentially reach masses of 50 to 100 solar masses, an intermediate step in a mass range called the pair instability mass gap, a range of black hole masses between roughly 50 and 130 solar masses that standard stellar evolution models predict should almost never be produced. Because stars in the right initial mass range either destroy themselves completely in pair instability supernova or produce lighter remnants. The existence of black holes in this mass gap has been one of the most heated debates in observational astrophysics over the past decade. And then, in September 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the merger of two black holes with masses of approximately 36 and 29 solar masses, producing a remnant of approximately 62 solar masses. That 62 solar mass remnant sits uncomfortably close to the predicted lower edge of the pair instability mass gap. And in May 2019, LIGO and its sister observatory Virgo detected the event GW190521, the merger of two black holes with masses of approximately 85 and 66 solar masses, producing a remnant of roughly 142 solar masses. The 85 solar mass progenitor sits squarely inside the pair instability mass gap. It should not exist by our standard models of stellar evolution, and yet there it was. A gravitational wave signature etched into the fabric of space-time, travelling from a source approximately 5.3 billion light-years away, arriving at our detectors as a chirp of geometric distortion lasting a fraction of a second. How did a black hole of 85 solar masses form inside the mass gap? One answer involves hierarchical mergers, smaller black holes merging in dense stellar clusters, building up mass stepwise. Another answer, more directly connected to R136A1, involves the possibility that our models of pair instability supernovae are incomplete, that under certain conditions, i.e. stars above a certain initial mass can partially collapse, retain mass, and produce black holes at masses we did not think possible through direct stellar collapse. R136A1 is, in essence, a living laboratory for exactly these questions. Some might wonder at this point whether all of this, the exotic physics, the theoretical uncertainties, the debates about mass gaps and merger histories, is purely academic. Whether the drama of R136A1's death, when it arrives, will be anything more than a spectacular light show for astronomers pointing their telescopes at the Large Magellanic Cloud. It will not be purely academic, not if you are within a certain distance. Let us talk about what a pair instability supernova would actually do to its cosmic neighbourhood. The Tarantula Nebula is approximately 160,000 light-years from Earth. This distance is significant. At that range, R136A1's eventual death, whatever form it takes, poses no direct physical threat to Earth. The radiation flux at 160,000 light-years from even the most energetic pair instability supernova would be far below the level required to cause significant atmospheric damage or biological harm. We would observe a spectacular event in the southern hemisphere sky. For weeks or months, depending on the scenario, a new object visible to the naked eye, perhaps rivaling the full moon at its brightest, and then it would fade. The light would pass. The shockwave, travelling at a few percent of the speed of light, would not reach us for millions of years, long after the shockwave itself had dissipated to insignificance. But the 160,000 light-year buffer we enjoy is not a universal constant. It is a specific, fortunate accident of our position in the local group. Consider what R136A1's death would do to a star system 100 light-years away, or 500, or even 5,000, at 100 light-years, a distance that encompasses hundreds of star systems in our own galactic neighbourhood, though not near R136 itself. A pair instability supernova at R136A1's predicted energy release would deliver a gamma-ray flux to any orbiting planet sufficient to strip the upper atmosphere and sterilise the surface. Not damage it, not stress it, sterilise it. The ozone layer of any Earth-like planet would be destroyed in hours, leaving the surface exposed to lethal doses of ultraviolet radiation for years as the ozone layer slowly rebuilt itself, if it rebuilt itself at all. At 5,000 light-years, still very local by galactic standards, the effects are less catastrophic but still significant. Enhanced X-ray and ultraviolet irradiation, potential disruption to atmospheric chemistry, a global spike in cosmic ray flux that could last centuries as the supernova remnant propagates through the interstellar medium. And the Tarantula Nebula is not alone. There are massive stars scattered throughout the Large Magellanic Cloud, throughout the Milky Way, throughout every galaxy in the observable universe. The nearest extremely massive star candidate in our own galaxy is Eta Carinae, at roughly 7,500 light-years, well outside the sterilization radius but within the range of meaningful energetic effects. Eta Carinae, at an estimated 100 to 150 solar masses, and already demonstrating the kind of instabilities that precede extreme stellar deaths, is a candidate for a hypernova or pair instability supernova within the next 100,000 years. Possibly sooner, possibly much sooner. At 7,500 light-years, the gamma-ray burst component of such an event, if Eta Carinae's rotation axis were pointed toward Earth, which current observations suggest it is not, could potentially cause mass extinction-level damage to Earth's ozone layer. Current orientation analyses suggest the risk is low, but not zero, not negligible enough to dismiss entirely. The universe, it turns out, has always been more dangerous than it appears from the gentle blue surface of our planet, and R136A1 is the most extreme embodiment of that danger we have ever directly confirmed. But understanding R136A1 only as a threat misses something essential about its nature, and about what its existence tells us about the universe we inhabit. Consider what R136A1 is making right now, in the nuclear furnace at its core. stellar nucleosynthesis, the process by which stars forge heavy elements from lighter ones through nuclear fusion, is the mechanism responsible for virtually every atom in your body heavier than hydrogen and helium. The carbon in your DNA, the oxygen in your lungs, the iron in your blood, the calcium in your bones, all of it was synthesized in the cores of stars that lived and died before the solar system formed, scattered into the interstellar medium by their deaths, incorporated into the molecular cloud that collapsed to form the Sun and its planets 4.6 billion years ago. You are, in the most literal possible sense, the recycled material of dead stars. But different elements are forged in different stellar environments. Carbon and oxygen are produced in intermediate mass stars, silicon and sulfur in more massive objects. Iron, the termination point of ordinary stellar fusion, the element whose production marks the beginning of the end for any massive star's nuclear burning sequence, accumulates in the cores of massive stars in their final stages of evolution. And then there are the elements that cannot be produced in any of these environments. The heaviest elements, gold, platinum, uranium, thorium, require conditions more extreme than ordinary stellar fusion can achieve. They require neutron-rich environments, explosive timescales, and particle densities that cannot be sustained during normal stellar burning. For decades, the astrophysical community debated their origin. The leading candidates were neutron star mergers and certain extreme classes of core collapse supernovae. A pair instability supernova at the energies predicted for an object like R136A1 represents a different and poorly understood endpoint of heavy element production. The explosive nucleosynthesis in such an event, the rapid production of elements in conditions of extreme temperature, pressure, and neutron flux during the moments of explosive burning, may produce abundance patterns of heavy elements that differ from those left by core collapse events. Studying the chemical fingerprints left in ancient, metal-poor stars that formed from gas enriched by the first generation of pair instability supernovae, has become a way of probing the very first stellar deaths in the universe. In the oldest stars we can observe, the chemical fingerprints are there, anomalous abundance ratios, missing elements, overabundances of others, the signatures, however faint, of a different kind of stellar death. The deaths of the universe's first monsters, encoded in the spectra of stars nearly as old as the universe itself. R136A1, when it dies, will add its own chemical fingerprint to the Large Magellanic Cloud. The elements it has forged, the products of its brief and furious nuclear burning, will be dispersed across dozens of light-years of interstellar space. Some fraction of that material will eventually be incorporated into new stars, new planetary systems, new molecular clouds cooling toward the conditions necessary for star formation. The violence of R136A1's death is, simultaneously, an act of cosmic enrichment. This raises an even bigger question. If stars like R136A1 are responsible for seeding their environments with the heavy elements necessary for planetary formation, and ultimately complex chemistry, then the places in the universe where such stars form and die are not merely dangerous environments. They are, on the right timescales, potential nurseries. The very violence that makes them lethal in the near term makes them generative over millions and billions of years. Is there a tension between the destructive and creative roles of massive stars? Absolutely. But the universe has never been particularly interested in resolving its own paradoxes. Consider the Tarantula Nebula itself, the star-forming activity visible there today, the hundreds of young stellar systems embedded in the 30 Doradus region, the compact clusters of O-type stars ranging from a few solar masses to several tens of solar masses, the complex network of ionized gas filaments, is not happening in spite of R136A1 and its cluster siblings. It is happening, in significant part, because of them. The stellar winds and radiation pressure from R136 have compressed the surrounding molecular gas, triggering the collapse of new stellar nurseries at the edges of the evacuated bubble. R136A1 is not just destroying material, it is arranging material into the configurations from which new stars will be born. This is the stellar ecosystem writ large. Massive stars form from molecular clouds. They burn furiously. They irradiate and sculpt the surrounding gas. They die in explosions that disperse their processed material and shock compress new regions of star-forming gas. The next generation of stars forms from this enriched compressed material. Some of those second-generation stars will also be massive. They will repeat the cycle, and embedded in that cycle is the gradual multi-generational process of chemical enrichment that has, over 13 billion years, transformed a universe of hydrogen and helium into a universe containing everything on the periodic table, everything in your body, everything that makes planetary surfaces and biospheres possible. R13601 is a node in that process, an extreme node. A node whose eventual death will be among the most energetically significant stellar events in the local group of galaxies for millions of years in either direction. But a node, nonetheless, in a process that is ultimately oriented toward complexity. What other monstrous stars lurk in the universe that we have not yet found? R13601 is the confirmed mass champion. But the confirmation comes with an asterisk. Direct mass measurements of stars require specific observational conditions, ideally membership in a binary or multiple system where orbital dynamics can be used to constrain individual masses. R13601's mass estimate comes primarily from spectroscopic analysis and stellar evolution modelling, calibrated against its luminosity. The uncertainties are not negligible. Yes, published mass estimates range from approximately 150 solar masses on the conservative end to over 300 solar masses on the more aggressive end of the theoretical parameter space. And the universe is large. The Large Magellanic Cloud is a small satellite galaxy. The Milky Way is substantially larger, and our view into its densest, most active star-forming regions is obscured by intervening dust. The galaxies beyond our local group are accessible to us only in their most luminous manifestations. How many R136A1-like objects exist in the observable universe, buried in dense clusters, hidden by dust, too distant to resolve from the local environment? The honest answer is, we do not know. What we do know is that observations with the James Webb Space Telescope, launched in December 2021, and achieving full scientific operations by the summer of 2022, are beginning to change the terms of that question. JWST's infrared sensitivity and angular resolution represent a leap in observational capability that is difficult to overstate. Where Hubble, operating primarily in optical and ultraviolet wavelengths, could resolve individual stars in the core of R136 only with difficulty, and could not peer through the dust veils shrouding many of the galaxy's most extreme star-forming regions. JWST operates at wavelengths that pass through dust more readily, and with a mirror large enough to achieve angular resolutions that would have been considered aspirational fiction a generation ago. Early JWST observations of star-forming regions have already revealed massive stellar populations that were previously invisible. The Carina Nebula observations released in 2022 showed hundreds of candidate young stellar objects embedded in dusty pillars, objects whose masses and properties are still being characterized. Observations of the Tarantula Nebula itself, released in September 2022, resolved stellar populations at the outskirts of R136 with unprecedented clarity, revealing dozens of previously unknown massive stars in the cluster and refining the population statistics for extreme stellar masses. The full census of massive stars in the local group is still being taken, and with every new observation, the upper end of the mass distribution is looking somewhat more populated than our prior models predicted. What does this mean for our understanding of stellar evolution more broadly? It means that the physical processes governing the formation of the most massive stars, the accretion dynamics, the feedback mechanisms, the metallicity dependence, are not as well constrained as we thought. The universe is capable of building things closer to its theoretical extremes than our models comfortably predicted. And if the universe can build R136A1, what else can it build? The theoretical maximum stellar mass, the Eddington limited mass above which no star can in principle form, is not a fixed clean number. It depends on metallicity, on the geometry of accretion, on the detailed microphysics of radiative transfer in stellar atmospheres. At zero metallicity, the theoretical maximum could be as high as 1,000 solar masses or beyond. In the early universe, when conditions were radically different from today, the formation of such objects was not merely possible. It was, according to some models, probable. We have never observed a star of 1,000 solar masses. We have never observed a population 3 star. but the universe is 13.8 billion years old, and our observational capabilities are only now reaching the point where the first generation of stars might be within our grasp. JWST's ability to detect the photons of early universe sources, shifted by cosmic expansion into the infrared, arriving at our detectors after a journey of 13 billion years, may eventually allow us to directly constrain the properties of the first stellar generation. We are, for the first time in history, building instruments capable of looking back far enough to see the universe before it became familiar, and what we find there will either confirm our models or shatter them. R136-1, in this context, is not just a remarkable individual object, it is a calibration point, a foothold. The most extreme star we can currently study in detail, providing a testbed for theories that extend to objects far beyond it, objects that shaped the early universe in ways whose echoes we are still deciphering today. As we continue to expand our observational reach with JWST, with next-generation ground-based telescopes like the Extremely Large Telescope, currently under construction in Chile's Atacama Desert, with future gravitational wave observatories of unprecedented sensitivity, the physics encoded in R136A1 will become increasingly legible. The uncertainties around its mass will narrow. The models of its eventual death will be constrained by comparison with newly discovered pair instability supernova remnants. The relationship between extreme stellar masses and the chemical enrichment history of galaxies will come into sharper focus. And one day, perhaps within this century, we will watch a star like R136-1 die. Not this one, not R136-1 itself, which will likely survive for at least another million years, but something like it, in a galaxy close enough to observe in detail at the right moment in its evolution. We will witness a pair instability supernova in real time. We will watch a star more massive than anything in our immediate galactic neighborhood erase itself from existence in a blaze of energy that briefly, spectacularly, outshines everything around it. And when that happens, every piece of physics we have assembled from studying R136-1, every spectroscopic measurement, every luminosity calibration, every contested mass estimate, will suddenly have a moment of direct observational validation, or refutation. Science allows for both. We began with an impossible star, a star that should not exist by the rules we thought we understood, a star so massive it defies the theoretical ceiling physics set for it, a star that burns with the light of nearly 9 million suns, sheds the mass of entire worlds on human timescales, and will end its existence in an act of destruction so complete that no remnant will survive. R136-1 is not a curiosity, it is a confrontation with the limits of our models, with the violence embedded in the most fundamental processes of the universe, and with the unsettling realization that the cosmos is capable of excess that our frameworks were not built to accommodate. And yet, there it is, burning in the core of the Tarantula Nebula, 160,000 light-years away, catalogued and measured and argued over in papers with long author lists and careful uncertainty estimates. Real. Confirmed. Indifferent to the discomfort its existence causes. We have traced its origin, a metal-poor environment that relaxes the brakes on stellar mass accumulation, an echo of conditions that dominated the early universe. We have followed its present, the relentless self-destruction of a stellar wind ablating solar masses into the surrounding void, reshaping the nebula, triggering new star formation, irradiating everything within range. We have mapped its future, the pair instability, the explosive burning, the possible total annihilation of an object once more massive than 200 suns, leaving behind either an expanding shell of enriched ejecta or a black hole of such mass that it sits in a region of parameter space our models treat with uncertainty, bordering on unease, and we have seen what R136-A1 represents beyond itself, a window into the first stars, a calibration for our models of stellar death, a data point in the ongoing effort to understand how the universe builds and destroys its most extreme constructions. One thread remains unresolved, deliberately because the universe has not resolved it either. We do not know exactly how R136-A1 will die. The theoretical predictions diverge at the very upper end of the mass distribution: pair instability supernova, hypernova, direct collapse. pulsational shedding followed by a muted final explosion. The models disagree, and the observational record of events at this mass scale is thin. Somewhere in the universe, right now, a star like R136A1 is reaching the end of its life. Its core is heating toward the pair instability threshold. The gamma rays at its center are beginning to convert into electron-positron pairs. The support is failing, and we may not know it has happened until the light reaches us. Thousands, millions, perhaps billions of years from now. The universe does not announce its most violent acts in advance. It simply acts, and leaves it to us, these brief, curious, carbon-based witnesses, to piece together what happened from the light that arrives in our absence.